To be literal does not mean that we cannot address scientific experiment. If we do our research and work together, we will have wonderful results that satisfy our instructors and impress our friends.
We searched, we studied, we shared ideas. Let's go agree to results.
In 1999, two researchers in Ernest Rutherford's laboratory at the University of Manchester has Giger and Ernest Martin fired a beam of alpha particles at 10 meters for alpha particles had been identified and named. They were called alpha rays to begin with, a decade earlier by Rutherford as one of the types of radiation given off by radioactive elements such as uranium. Being fast-moving and positively charged, they now known to be light-speed helium nuclei. Rutherford reasoned this served a good probe of the atomic structure of matter.
According to one popular theory at the time, championed by G.G. Thomson, atoms were built along the lines of current bands, with electron particles carrying negative charge for a current and smeared out positive charge for the rest of the band to keep the whole thing electrically neutral. Of the current band model, were write every one of the alpha particles out to zip straight through the thing foil in Giger and Marsden's experiment, suffering at most minor deflection because of the weak influence of the spread out positive charge. The effect of electron being negligible. What Giger and Marsden actually found was stunning. Most of the alpha particles did indeed travel straight through the foil with light or no deviation, but a small fraction, about 1 in 10,000, rebounded, ending up on the same side of the foil as the incoming beam. A few were returning almost along the same tracks as they went in. Rutherford described hearing of this rebound as the most incredible event of his life. It was, he said, as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. Such a huge deflection could mean only one thing: some of the alpha particles had ran into massive concentration of charge, and since like charge rip had been hurled straight back by them. Thomson's current band model of the atom, in which positive charge was spread thinly over the whole atom, hadn't a hope of explaining the result.
Instead, in 1911, Rutherford cooked up a new model of the atom in which all of the positive charge is crammed inside a tiny massive nucleus about 10,000 times smaller than the atom as a whole. See figure 2. That's equivalent in scale to marble in the middle of a football stadium. The much lighter electron, he assumed, lie well outside the nucleus. To the shock and amazement of everyone, the atoms of which planet, people, pianos, and everything else are made consist almost entirely of empty space. Rutherford's nuclear model of the atom was a huge step forward in understanding nature at the ultra-small scale, but even as it closed the casebook on the alpha particle experiment is through open another one, since the nucleus and its rich union of electrons are oppositely charged and therefore attracts one another. That didn't seem anything to stop the electron from being imbued immediately into the nucleus through the new universe atomic matter. Out to implode in the wing of an eye. Rutherford countered by saying that the atom was like a miniature solar system. The electrons circled the nucleus in wide orbits just as planets orbit the sun. This is the picture of atoms that most of us still carry around in our head. It's a plain, easy to grab image on that inspired many logo of the atomic age. Yeah, theorists were well aware of its shortcomings right from the start. The fatal flaw in Rutherford's model is that it contains charges that are accelerating. The charges are on the electrons, and the acceleration is due to the electrons always changing direction as they move around their orbits. Things accelerate when they change speed and or direction. Since Maxwell's style, scientists had known that accelerating charge radiates energy. What was to stop the orbiting electrons in Rutherford's atom quickly, in fact, in about 100 million of seconds, losing all their energy and spiraling into the nucleus? The answer came from a young Daniel Bohr, who joined the team at Manchester from a 6-month spell in 1912, shortly after Rutherford went public with his new vision of the atom. Bohr played a hand he knew about Planck's quantum. He knew there was no way to save an electron inside an atom from plummeting into the nucleus if it could give off energy continuously, and so he said simply, the electrons inside atoms can radiate continuously. They can only radiate in lamps, and these lamps are the same as Planck's quanta. For a given type of atom, say hydrogen, there's a limited number of stable orbits. Then an electron can occupy each of these orbits corresponds to a whole multiple of the basic quantum. As long as an electron is in one of these orbits, its energy, contrary to whatever classical physics might say, stay the same if it jumps from an outer higher energy orbit to an inner lower energy orbit. The energy difference between the two is given off as a quantum of light. Once the electron reaches the lowest energy orbit, it can't fall any further and is safe from the clutches of the nucleus.
While performing experiments on radioactivity, Ernest Rutherford bombarded fast-moving alpha particles on a thin gold foil. He observed the reflection of the alpha particles with the help of a screen. Now, according to Thomson's atomic model, an atom consists of a positively charged sphere with electrons embedded in it. So, Rutherford expected that almost all the alpha particles will pass straight and only small deflections will be observed if there would be any. However, Rutherford got totally contrasting results. From his experiment, he made the following observations. First, most of the fast-moving alpha particles passed straight through the gold foil. Second, some alpha particles were deflected through the foil by small angles. And the third point, some alpha particles were deflected by large angles. In rare cases, an alpha particle got deflected by an angle of 180 degrees. Based on his observations, Rutherford derived the following conclusions from his gold foil experiment. First, since most alpha particles passed through the gold foil without any deflection, most of the space inside an atom is empty. Second, very few particles suffered a deflection from their path. Now this means that positive charge occupies very little space inside an atom. Third and final point. As a small fraction of particles got deflected completely by 180 degrees, all positive charge and mass of gold atoms are present within a very small volume inside the atom.